What's up? This is the beginning of this new series. I have no idea what I'm going to call it. Something like Illiterate Calculus BC student teaches calc concepts. And this is our first episode. Today we are going to be explaining arc length, which is a very interesting concept, at least to me. We're going to explain the foundation and basically how it is derived. So let us make a function. This function has some length. If you stretched it out over the length of its entirety, it would have a definite length d, or L. Let's actually call it L. And in calculus, the easiest way to really find any definite area, or definite anything basically, is by separating it into some subsections. So we'll make some subsections right here. Boom. Bam. Wow. Those are some definitely equally spaced subsections that are very amazing. Very well built. So this has a length. Let's make that a little more straight. It's actually almost already a straight line. I did not mean to do that. This is a line. This is a line. This is a line. And this is a line. And to be honest, this is annoying me a tiny bit. We'll make this a tiny bit longer. And we'll do that. And yeah, we'll make one more. One more right here. Boom. Wow. Okay. So what should we call these subsections? We can call them portions, I guess. This will be P0. And then this part will be P1. This will be P2. This can be P3, P4, P5, P6. Boom. And we want to know what the length of each of these subsections are. And the length of the subsection will be a sum of all of these subsections. We'll say L is approximately equal to the sum of I equals 1 P I minus 1 P I. And you may be asking me, what the fuck does this mean inside of this? Well, it's actually just a very small simplification. Pi minus 1 times Pi is equal to the change in x squared plus the change in y squared square rooted, which we can write like so. This will take a little bit to do. Y minus 1 squared. There you go. And this is derived from, obviously, the Pythagorean theorem. This arc length has an x and a y. I mixed those up, x and y. And it's change in x, which is the length of our sublevel, plus the change in our y, which would be from p, which would be the function when it is the function of I minus 1 to the function of I, the change in y, equals our length squared. And then our length is equal to the square root of x squared plus y squared. If you're a calculus student, you didn't need to know that. I don't know why I really explained it. But, yeah. This is our formula. We can simplify this right here by saying our change squared plus our change squared. And simply saying our length is our length. Amazing. And the idea is, as you get infinitesimally small with these subsections, you will get closer and closer to our L. Okay, so the mean value theorem. Everyone loves MTV. We'll just write it as MTV. Everyone loves MTV. And in this instance, we can say that for some value on the interval xi minus 1 to xi, there is a point x so that f x I minus f x I minus 1 equals the derivative of x of that specific point. This is what we'll call the specific point, by the way. We'll just call it x. There's no reason to fuck around. No, there's no reason to muck around. Okay. And such that the derivative of f prime x times xi minus 1. Bam. So these two should equal each other. And I think that a simpler way to write this would be that this f of xi minus f of xi minus 1 is equal to the change in y. And the change in y equals the derivative. I cannot write f prime x times the change in x. So y over x times x equals y. And y equals y. Very cool. Very cool what we just did. We just proved a very simple mathematical concept, but it's very useful. The reason it is useful is because we now know that we can plug in. What can we plug in? See, there's a first time for everything. So we know in our original formula pi minus 1 times pi, that's not what it's not times, by the way, that's just what we labeled it. We can now say that this right here, xi minus 1 squared, is our change in x squared. That's very useful. And we can say that this would be plus, we know that f of xi minus f of xi minus 1 equals f prime x times xi minus 1, right? This right here is our change in y, yi minus 1, and that's squared in our length of the subinterval. So what we'll end up seeing is that we can now plug in this function, f prime of x, xi minus xi minus 1. And this is all squared. So now we can write this as, we should probably go slightly to the left because we have so much space. We can now write this as the square root of the change in x squared, I cannot write accurately enough, plus f prime x, and then this xi minus 1 squared is the change in x again, change in x squared. So we now know that our length function is equal to this very specific value. And this very specific value, as you can see, the change in x squared is seen both, let me change the color, both here and here, which means that we can now take out our change in x. This equals the change in x times the square roots of 1 plus f prime x squared. That is revolutionary. Now our exact length will become L equals the limit as n approaches infinity. Let me just write the little sigma, boom, I equals 1, p I minus 1, p I equals the limit as n approaches infinity, the frickin' square roots. I excluded our sigma. It's going so bad. See, there's a first time for everything. We're using the Khan Academy software. I could even give you a link to it in the bio. I don't even know what it's called. I think it's the bio. F prime x squared, boom, times the change in x, which is the definition of our sigma notation for an integral. So we come down here and we can now say that, actually we don't need to write the integral yet, that L is equal to the integral from a to b of the square root of 1 plus f prime x squared times the change in x. And this is revolutionary. Guys, we just solved for the arc length of any function that exists in the history of the world. You can measure the length of anything, any line, any parabola, anything, just by knowing this formula. Absolutely amazing, absolutely sick, absolutely cool, and a very much simpler way to write this would be, it's a lot more convenient for our process, would be 1 plus the change in y over the change in x squared dx. It's also the exact same. It doesn't change anything at all. But whatever. let's see. Okay, I think what we can do to prove that this exists is to plug it into some very simple function. Let's get y equals x. I'm reading like hieroglyphics right now. What is going on? Okay, y equals x. Whatever, I didn't make it any better. Y equals x. We know that as x changes, y changes. And what we'll see in whatever length n that we get in the x direction, we will also get upwards in the y direction with the same length n. And this will make our favorite isosceles right triangle that will have lengths of n and our long side being the square root of 2 times n. So anytime that x changes, we can see our arc length should, in theory, using this formula, change by square root of 2 times n. So let us plug it in. I think this is the very bottom of my doc. Okay, we can make our space this way. The integral of the square root of 1 plus d over dx x squared dx should equal square root of 2x. And what we'll see is, what is the derivative of x? It's 1. And we'll see the square root of 1 plus 1 squared integrated dx equals the integral of the square root of 2 dx equals square root 2 x plus c. And boom, bam, bop. That is exactly what we derived. Now, let's use this for something really stupid. Have you ever thought in your life, I need to find the arc length of a circle from its radian value, and it's a unit circle? You definitely have not, because that's really stupid. But let's do it. Solve for y, 1 minus x squared. Then we can say y equals plus or minus the square root of 1 minus x squared. And now we can integrate this bitch. I don't think I can say that on my school account, but we do not care. We are going to plug square root of 1 minus x squared into this function. Now we need to know, what is the derivative of 1 minus x squared? Well, we can write it as 1 minus x squared to the 0.5. Wow. I want to see Paul Allen's card. Okay. 1 minus x squared times negative 2x. Negative 0.5. And it should end up being x over the square root of 1 minus x squared. I'm pretty sure the derivative of that is x over the square root of 1 minus x squared. However, I'm a little bit rusty from Christmas break. It's New Year's Eve. It's 7 in the morning right now. So I'm pretty sure we got it. But for the purposes of our thing, we should just check. I'm too lazy to edit it. I'm just going to keep talking, so you aren't bored. And say your shoe size in the comments. It's actually negative. So, oh yeah, because, okay, I'm stupid. So when we chain rule it, the square root goes to the bottom, you'll see the negative come in. So yes, you end up getting the integral of the square root of 1 plus, be very careful, negative x. The negative doesn't even matter, so I could have just ignored it even with the mistake, squared dx. Cool, cool, cool. Equals the integral of the square root of 1 plus x squared over 1 minus x squared. And okay. This could be a very hard integral, but this 1 makes it actually a very easy integral, I believe. The 1 will turn into a 1 minus x squared on top, plus x squared over 1 minus x squared. We'll see these cancel out, and we will end up getting, we'll just go to the top here, we'll end up getting, sorry if it's hard to follow, hopefully you're taking notes at home, because I am an absolutely amazing calculus teacher. You'll get the integral of the square root of 1 minus 1 minus x, 1 over 1 minus x squared dx. Now, this, I believe, sorry, I have not done this problem before. I believe we can do sunscreen voodoo. And sunscreen voodoo is, you'll get uv minus v du equals the integral. And we'll just do some u substitution. And bada bing, bada boom. I do not. Sorry, let me think about this. I think this. Wait a minute. I might have done something wrong, because we can just rewrite it as this, and that becomes arcsine. So now we just have, so the 1 minus x squared in square roots, this is an arcsine function. It's a over the square root, I don't remember, a squared minus x squared, I believe. And, okay, so this integral equals arcsine plus c. Very cool. So the integral of our function, our arc length from, I guess this would be just one-sided. This would be from, let's just say, A to B. So we have our function. We turned it into, by the way, we turned it into a half circle, a semicircle, because when we did we did like a shell method on it. We turned it into a square root, and it cut off the bottom part of the y. So let's say from freaking we'll change it to red, A to a little purpley blue that we're just gonna call B. Always remember your plus C's, by the way, right here. I don't know what I'm yapping about, but apparently we did it. I may have made a mistake because I did not expect to get arcsine. So now the integral of our arc length, which should be ending up being pi over 4 if we plug in pi over 4, should be our angle. So wait, if we plug in so now our arc length is pi over 4. I actually think I solved for the wrong thing. Because now we have arc sine pi over 4. Let's say this length is equal to pi. This would be pi over 2. I don't know what I'm talking about. I'm yapping. This length, if this was a 90-degree angle, would be from A to B. It would be pi over 2. And arc sine of pi over 2 is 1. No, it's not. What am I talking about? We'd say arc sine of 1. We'd say arc sine of our value, our chain. I think this would be our... I don't even know what I just solved for, dude. I haven't slept all night. What is going on right now? What am I yapping about? Oh no. Oh no. Oh no. It's over. It's over for us. It is absolutely over. This would be from 0 to 1. So it would be arc sine 1 minus arc sine 0 equals pi over 2. So what I meant to solve for was our arc length. I was trying to have the arc lengths equal each other, and it would be funny. But I'm stupid and illiterate, as the video will say, and I accidentally solved for our degree angle, which is pi over 2. I did just solve for exactly what I wanted to solve for, because pi over 2 is equal to the angle that we plug in at the beginning, which would be pi over 2, and they would equal each other. So guess what? We just solved for how many radians is in our radian angle between A and B using way too much math. Woo! Oh, we had more space at the bottom. So this was a success, and now you have to watch me play freaking chess. Also, shout out to OBS Studios. Shout out to Lee Chess, because we are about to win a 10-minute game of chess. Imagine if I could spell my password. I actually don't remember what it is. I got it. I'm a genius. And, you know, sometimes it takes a genius to win a game of chess at 6:55 in the morning. Okay, I'm back. Create a game. I haven't played a game of chess in so long. It's actually now has a question mark over my rating. And yeah, let's see if someone will play my 10 by 15 that I just put up. I really hope you guys enjoyed this video. It appears I don't think anyone's gonna play it. At least not quick enough for me to not have to edit this video. So we just took it off. That is the end of this first episode of How to Solve for Arc Length, Introduction to Arc Length, Illiterate Calc BC student in Mr. Sproul's class, period 6. Teaches you calculus concepts. Have a good day and a good New Year's Eve. Buy some Woody hoodies on eBay. Quinchio Chios. Bye.